What's going on, everybody? Let's talk about integrals, okay? So conceptually, think about integrals as approximating the area under the curve of your function, okay? So say I give you this as the trend or the curve of some function f of x that goes from x is equal to a, right, which is this point, and it goes until this point where x is equal to some point or some value b. The area that we're referring to is this, right? This white space that's in between this function, f of x, this trend line, and the horizontal x-axis. And so when we're considering areas under the curve, I want to specify that if your function f of x, same curve, right, is above this horizontal x-axis, the area under the curve is this space here. And since it is above the x-axis, this is considered a positive area, okay? Whereas if you have even the same trend line or the same curve that's located here, the area under the curve that we're considering between A and B, and I forgot to write that, between A and B, in this case, it's going to be this white space, right? And so really the area under the curve will always be the white space or the area between the curve of your function and the horizontal x-axis. In this case, this is going to be considered a negative area because it is under the horizontal x-axis, okay? So this is going to be negative. So keep that in mind when you're doing your calculations. And so one method, or the way in which we're going to approximate the area under the curve, is we are going to take the entire area, right, the entire blank space, and we're going to break it up into what we call subintervals, okay? And so we're going to use the same function here, and so this is the function here, right? And still it's going to be between some value x is equal to a, and it's going to end at some value x is equal to b. And in this case, we're going to break our interval, right, into four subintervals, right? So n subintervals. In this case, we're going to break that into 4 subintervals, and it's going to be between a and b, right? A and b. And so if we're looking at a single subinterval, a single one of these rectangles, let's say this is what represents a single subinterval. If we want to figure out what is the width, right, of one of these subintervals, and they're all going to be the same because we broke them up into 4 even subintervals, the way that we can do this is simple. We can consider the entire interval from a to b. We're going to do that by subtracting b minus a, right, to just get this interval here. We're removing this part, right, by subtracting. And we're going to divide that by the number of subintervals that we want to break it into. In this case, it's 4. And so this is going to be the equation you use to figure out the step or the delta x of each of your subintervals, okay? And so once you've calculated this delta x, right, we can look at the definition or the formula for a derivative, and that's going to be over here. So if you look at this term, right, interpret this as the integral or the area under the curve on the interval starting from a, right, starting from a, ending at b, of some function f of x, right, of some function f of x with respect to x, right, with respect to the x-axis. And so you can calculate this by using this. So we're going to evaluate the limit right? We're going to evaluate the limit as n approaches infinity, right? And this is a summation, so you haven't gone over summations yet. Go look over that first and then come back. But it's going to be the limit as n approaches a very large value, right, of the summation from I is equal to 1 to some large number of f of x, right? Let's break this down. Let's look at this side, okay? And so if we're just looking at the right side of that equation, right, let's look at this. Limit as n approaches infinity, summation I is equal to 1 to n of some function f of x delta x. So based on what we said here, how we can calculate the step or the change, right, the width of each of the intervals, this is going to end up being a number, right, a number value, because b is going to represent some larger value of x, a is going to represent some smaller value of x, and then n is also the number of subintervals. So this, in a sense, is a constant. Okay? And so just like you did in derivatives, even when you're doing summations, you can move constants out in front of your summation and just multiply it back in later after you finish your calculations. So this can be simplified to this. The limit stays the same, right? Delta x, this is going to end up being a numerical number. And then this is the only part you really have to worry about. Computing the summation from I is equal to 1 to n of your function. And so just to kind of go over this more specifically, right? Let's do an example. And so before we do that though, I almost forgot. By looking at our subinterval, right? We're going to be able to approximate using either a left-handed sum, right? Or a left endpoint, sorry, or a right endpoint. And I'll show you what we mean by that in context, okay? And I'll get rid of the hand part because that's a little bit weird. So left endpoint, right endpoint, and let's get into that. Okay, so let's look at this example. Okay, evaluate the Riemann sum for this function. F of x is equal to x cubed minus 6x. Taking the sample points to BB, right endpoints, right? So you're dealing with right endpoints. And you're also given the interval A, B, and the number of subintervals. All right, so this is what we're going to do first. So just to get an idea of what we're expecting in terms of approximating the area under the curve, right? We are going to plot our function, this function, over the interval that we're considering. So from 0 to 3, right? From x is equal to 0 to x is equal to 3. And so the area under the curve that we're really talking about in this case is this area, right? The area between the f of x curve and the horizontal x-axis. And also this area. Because on the interval from 0 to 1, 2, about 2.5 maybe, the area is going to be negative, right? Because it's under the horizontal axis. Up here, it's going to be a positive area. But we do notice that the negative area is going to dominate this calculation. And so overall, we're going to expect a negative approximate area, okay? And so let's do that. So we can first calculate our delta x, right? Because delta x, remember, is calculated by considering our entire interval and dividing it by the number of subintervals that we want. In this case, these values were given to us. So b is equal to 3, that's our endpoint, minus 0, that's our starting x point, divided by 6 is our number of desired subintervals. And so that's going to give us 3 over 6. So in the end, that's going to give us a delta x of 1/2, or 0.5. Right? And so now we have how many units we're going to change every time we go to the right. So what this is going to look like is this. Let me see if I can neatly divide this into the subintervals, okay? So we're going to have one rectangle here, one rectangle here, and these are all going to be the same thickness with the same width if this were a perfect picture. So I apologize. Another one. Another one. Okay. This is going pretty well, actually. Another one. And then another one. Okay, so 1, 2, 3, 4, 5, 6. 6 subintervals. We did it. We did it. 6 subintervals. So now, every time you go from one edge of a subinterval, right, to the next, to the next, to the next, each jump is going to be, right, 0.5. That's your change in x every time you move to the right, 0.5. And so, because they're asking, or this question is asking you to use the right endpoints, okay, as your sample points, right? What that's telling you is that you're going to use not the left endpoint of each rectangle, but you're going to use the right endpoint of each rectangle, right? So you're going to end up using this one, and then this one, and so on. Okay? And then you're going to end up using this one. So you have 1, 2, 3, 4, 5, 6, right? That's correct because n is equal to 6. And so let's map out your sample space. Okay, so x is going to be a range of your sample space. I will label this your sample space. Okay, and this is going to include 0.5, right? Because 0.5, 1, 1.5, 2, 2.5, and 3. Okay, so 1, 2, 3, 4, 5, 6 values. So that's right because n is equal to 6. And so now we can evaluate. All right. So if we are trying to approximate the area under the curve based on these subintervals, these rectangles, right? So we can approximate the Riemann sum of these 6 subintervals and calculate that as the summation from 1 to 6, right? Because we have 6 subintervals. So from the first subinterval to the 6th subinterval, we're going to calculate the sum of all those areas and add them together based on our function, right? Multiplied by our time step. Okay, sorry, not time step, but our delta x. Sorry about that. And so it's going to look like this. Again, delta x is 1/2, right? We already found that. So delta x is a constant that we can move in front of the summation and multiply it back in later. And so we're going to have delta x. I'll just fill it in as 1/2 because that's what it is, multiplied by this, right? Multiplied by, and then I'll actually write what it means now. Sorry about that. It's going to be 1/2 multiplied by the function evaluated at all of our sample space points. So f evaluated at x is equal to 0.5, right? Plus f evaluated at x is equal to 1, plus f evaluated at x is equal to 1.5, and so on until you get to the end, right? F evaluated at 2.5 plus f evaluated at 3.0, okay? And so this is the calculation that's going to give you the approximate area under the curve. And so 1/2 multiplied by the total, whatever you get from this calculation. And so if you put that into a calculator, and remember that the function that we are talking about is this one right here, right? So for all of these, evaluate this function, x cubed minus 6x, you're going to find that you get a final answer of, and then it's a lot of erasing going on, you're going to get a final answer of negative 3.93. Okay, so that's going to be the approximate area under the curve from 0 to 3 with 6 subintervals of your function x cubed minus 6x. And just as a sanity check, remember at the beginning, we said that the area under the curve had more negative area, right, this area, than the positive area. So our answer is negative, so it makes sense, okay? So if you understood that, let me give you a problem now to do, and then you can try it yourself, and then we'll get together and see if we got the same thing, okay? So take a second if you need to, and after this, we're gonna jump into part B of this, okay? And so let's evaluate that function, all right? And so we already have our sample space, right? So let me, for part B now, I'm gonna identify our key pieces of information, right? So we have our delta x. Using our delta x, we have our sample space, right? Our inputs based on a right endpoint evaluation, right? Based on these right endpoints. And we are going to use the formula that we saw before. And so let me open this screen and then I'll rewrite it, okay? So we are trying to, again, this is for part B now, we're evaluating this function, 0 to 3 of x cubed minus 6x dx, okay? And we said that we already calculated our delta x as 1/2 or 0.5, and that our sample space is going to be 0.5, 1, 1.5, 2, 2.5, and 3, okay? And so let's write this integral in terms of the definition or the formula. And so if we do this, the integral on the interval from 0 to 3 of the function x cubed minus 6x with respect to x is equal to the limit as n approaches infinity of the summation from I is equal to 0, ending at 3, right? Starting at 0, ending at 3, starting at 0, ending at 3, of our function multiplied by our delta x. And so we said that delta x is 1/2, it's a constant. That goes in front of the summation. And so we can rewrite this right side, and I'm going to keep it consistent. We can rewrite this right side as the limit as n approaches infinity of 1/2, because that's what delta x is, it's 1/2, multiplied by this summation from 0 to 3 of our function x cubed minus 6x. But instead of writing that, actually, I'm going to keep it as f of x so that it's going to be a little bit cleaner when you look at this. Okay? Getting jumpy with the pen. X sub I. There you go. Now, all we have to do is essentially evaluate this part. Okay? And so we're going to multiply whatever we get from here by 1/2. So you can write it like this, 1/2 multiplied by, all this stuff will go inside these brackets. And so all you're gonna do is evaluate your function, right? X cubed minus 6x at your sample points. So f of 0.5 plus f of 1 plus f of 1.5 and so on, plus f of 2 plus f of 2.5 plus f of 3. Okay, and when you put that into a calculator, right, and again I'll write this here, the function you're evaluating at this point is x cubed minus 6x, and that's where you're going to evaluate these, right? You're going to end up with a value inside the bracket of negative 7.875, which is going to end up being negative 3.93. Okay? And so that is how, again, that's how we're going to calculate the interval, just in the context of giving you this expression and telling you to evaluate. Okay? So if you are following this far, good job. If you're having a little bit of trouble, it's totally fine. Just pause and go back to wherever you're stuck. Now I want to give you an example to do, and then we can see if we get the same answer after you've worked it out. Okay? So now let me give you, is it this one? It is this one. So evaluate the integral on the interval from negative 3 to positive 3 of the function x squared with respect to x, okay? Using 6 subintervals and a left-hand sum. So different from last time, a left-hand sum. And just in case you're unclear on that, what I mean by that is that if this represents your subinterval, right, that square, you're going to use, instead of this point, right, that we did on the last example, you're going to end up using this point, or this x value for your sample space, okay? So go ahead and pause it and try it. Awesome. Let's see if our answers matched, all right? So let's get the obvious steps done and out of the way, okay? So given the information that we have, we know our interval, meaning we know our value for A, because we're starting at negative 3, right? We know our B value, our ending value, which is 3. And then we know that we want 6 subintervals. So based on this, we can calculate how thick or the width of our subinterval, okay? And that's going to be b minus a over n, which is going to be 3 minus -3 over 6, which is going to be 6 over 6. And so your delta x is going to be 1. Awesome. Okay? So looking at the plot, right? Because we know now this is a parabola. We know it pretty well. The area under the curve that we are considering is, right? It's going to be this, as well as this. Remember that the area, right? And it's okay if you messed up and you shaded this in, but remember that the area under the curve is that white space, or the area between the curve and your horizontal x-axis, okay? And so both of these are above the x-axis, and so we are going to expect that the area that we get is going to be positive, okay? And so based on this, we want to break our interval that we are considering into the proper number of subintervals. So let's do that in red. So, and these are supposed to be straight rectangles if it was perfect. Okay, so essentially we're going to have one here, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6 subintervals. And so now we are going to approximate the area, the summation of all the areas of these subintervals, to approximate this area. And so let's do that. Let's use our formula again, and let's do it. So the derivative, the integral, not the derivative, the integral from -3 to 3 of our function x squared with respect to x is equal to the limit as n approaches a very large number, infinity, right, of the summation from I is equal to -3, right, -3, ending at +3, right, of the function f of x multiplied by delta x. And again, delta x was already calculated, it's 1. This is a constant. So just like in a derivative, move that constant out in front of that sigma and just multiply it back later. So with that, we can rewrite the right-hand side as the limit as n approaches infinity of 1, because that's what delta x is, multiplied by the summation of, oh, I'm not going to rewrite it again. Let's calculate this out. Right? So 1 is delta x times the summation, this term right here, right, is what's going to go in here. Okay, and so in here we're going to evaluate f of x at all of our sample spaces. And so what are our sample spaces? Forgot to write that up here. Our sample space values of x, right? We know that our interval starts at -3, ends at +3. We have 6 of them, right? And every time you move to the right, that's 1 unit. So -3 goes to -2, goes to -1, goes to 0, and so on. Because we are taking the left-hand sum, okay? What we're talking about is the left hand, right? The left hand of each of these rectangles. So we're taking this as a sample. we're taking this as sample 2, this as sample 3, this as sample 4, this as sample 5, and this as sample 6. We do not take this one, right? We would only take this one if we were considering a right-hand sum. But even in the case of a right-hand sum, you would not take this one, right? Because this is on the left. So just make that clear for yourself, okay? So our sample space is going to be x is equal to -3, -2, -1, 0, all the way to +2. Okay? So you should have 6 of them. 1, 2, 3, 4, 5, 6, right? And so now you can evaluate your function, which is x squared in this case, right? At -3, add that to your function evaluated at -2 plus the function evaluated at -1 plus at 0, at 1, and at 2. All right? And so I will write this here. The function you're evaluating is x squared, right? X squared, x squared. And so when you do this, you're going to end up with 1, right? Because that's what delta x is, times stuff inside, which will end up being 55. And so your final answer, or the approximate area under the curve, right? Under the curve x squared on the interval from -3 to +3, considering 6 subintervals and a left-hand sum, is going to be 55. Okay, so if that's what you got, good job. If you're struggling a bit, totally fine. Go back and check on the places where you're confused, okay? If you guys have any questions, comments, let me know below and I will respond as soon as possible, okay? This was integrals, all right?